Hello, class. Okay, so we're going to talk about a device called a solenoid. I drew one here, but I have an actual solenoid here. Basically, it's just a cylinder, and yeah, if I hold up, you can see this is just one wire that's wrapped around it many, many times. And so you can run a current through it. And so I drew like here's our solenoid. And let's say, so this wire, it's one wire that keeps wrapping around this cylinder. And I drew it so the current's coming up here, loops around, goes in, then loops around and comes out of this next one, and just keeps going around and around. And right, so that's a device called a solenoid. And I drew a magnetic field, something like what the magnetic field looks like. There's a better picture. Got this whole book here. That's two pictures I'll hold up. One of them, imagine that the wires aren't spaced very closely. You can see you get some actual curl around the wires, but like in the middle, the magnetic field lines are kind of just straight down the axis. And another picture here, basically when you're in the middle of the solenoid, the magnetic field lines are mostly parallel, and then they spread out when you get near the edges. And we're going to consider a long solenoid. And so I'm going to erase the magnetic field line. Say we have a long solenoid, and the magnetic field lines we're going to assume are just parallel to the draw the wires again. And that determines the direction of the magnetic field. So again, if you just use the right-hand rule, look at one wire. The magnetic field lines circle around this way, so inside the solenoid they'd be pointing to the right. And similarly here, these go in, so they circle around like this. Inside the solenoid, the magnetic field lines are pointing to the right. And if it's a long solenoid, if we can ignore the edges, we get magnetic field that looks like this. Now, in reality, they're going to spread out because a solenoid has to have an end. But let's ignore the edge effects. And then we can talk about the magnetic field inside the solenoid. And we can solve this using either the Biot-Savart law, where our wire is this helix shape. That would be very difficult to do. But we're actually going to solve this using Ampere's law. So we're going to draw a couple Amperian loops. One of them, so magnetic field lines are parallel to the axis of the solenoid. But what about, how does the strength vary along, like, let's draw another perspective like this, where you're looking down the axis. Now, how does magnetic field line, like in the center compared to some other point there? And we can actually enter that using Ampere's law. So I'm going to draw a rectangle for our closed curve. So we have a rectangle here, and let's trace it this way. We'll go counterclockwise. And the magnetic field lines are parallel to the axis. So like this B dot ds along these two sides are going to be 0. Because the magnetic field, like here, is to the right. Along this segment, it's up. They're perpendicular to each other. And so B dot ds is B ds cosine theta. Cosine of 90 is 0. However, along these segments, these two segments, let's call this B1 and this B2. So B1 is, the magnetic field along this line segment, and B2 is a magnetic field along that line segment. So let's apply Ampere's law. Okay, now we have 4 segments. 2 of them are 0. And along these 2, well, along this, let's do B1 first, or this line segment with magnetic field B1. That's going to be B1 times L, where L is the length of this line segment. So the dot product, B dot ds, is going to be just B ds, no vectors. And because the magnetic field is going to be constant along this line segment, we can take it out of the integral. So we just get B1 times L. And then along this upper line, the magnetic field is to the right and the line segment is to the left. Or the direction that we're integrating is to the left. So we're going to get a minus sign, but otherwise it's the same. So we're going to have minus B2 times L. We can factor the L out. We have B1 minus B2 times L. So that's the integral, going all the way around that purple path. Now, according to Ampere's law, we did the left side. This is equal to mu naught I, where I is the current that is passing through this purple path. So this purple path has like this inside. It defines this area inside it. However, this is completely inside this hollow solenoid. And so the current passing through it is 0. And so this line integral gives us 0. And the conclusion is that B1 minus B2 is 0, or B1 equals B2. And so what we've shown with Ampere's law is that the magnetic field, let's say that this was B1 here, and B2 here, they're equal to each other. So it doesn't matter where you are in the solenoid. The magnetic field is parallel to the axis and constant in magnitude. It's an interesting result, certainly not something obvious. You might think when you get really close to the edge, you're close to the wires that are producing, at least some of the wires that are producing it, you might think it's stronger there. Or maybe you'd think it's stronger in the middle because it's the same distance from everything, but it turns out that it's constant everywhere inside. Because you can, move these lines around, just stretch this rectangle, and yeah, the result follows. Magnetic field is constant inside the solenoid. Okay, now let's go back to this perspective here. And let's draw an Amperian loop like this. Now, we're not going to do too much with this, but let's look at this integral, b dot ds, and this actually cannot be equal to 0. Let me hold this picture up again. We can see that there are magnetic field lines outside the solenoid in both of these pictures, but it looks like they're due to the fact that there is an edge, and we're that if we had, say, an infinitely long cylinder, then these edge effects then the magnetic field lines would just be parallel. Nothing would exist outside of the solenoid. But that's actually not the case, because this, looking at it from a different perspective, so like this is the same loop. We have this circle around it, but here, is there any current crossing this surface? And the answer has to be yes. There is. So again, this is one perspective, this is another, but there has to be some current crossing this Amperian loop. because this is just one wire that's winding around in this helical direction, so there has to be some current going to the right, the way I drew it. Like it winds around this way, and so there is some current, so there has to be a magnetic field outside the solenoid. And actually, we can evaluate that, and it basically you get like the magnetic field of a long straight wire. However, the magnetic field outside the solenoid is very weak compared to what is inside it. Because the current is mostly going, you know, like you can see these wires here. I don't know how well you can see them, but you know, they're very closely packed together. And so, you know, the current is mostly going this way. A very tiny component is actually crossing that surface. And so, even though it's not zero, it is very small. And it's small enough that we're going to state that the magnetic field outside the solenoid is zero. So again, a little bit of an approximation, but in practice, it works just fine. The magnetic field is much weaker outside compared to inside, so we can just disregard it. Okay, but now we want to find the, okay, so we know the magnetic field inside is significant, unlike the magnetic field outside the solenoid. We know it's constant in magnitude everywhere, but now we want to know what it actually is. And so, let's say our solenoid has a length L. Now, an important property is the number of, let's just leave it like that for now. Our solenoid has a length L, and I'm going to draw a loop like this. Yeah, get rid of this one. We don't need that anymore. So let's draw a loop like this. I want to actually trace it this way, because we can see the current is into the board here. So let's trace it that way so we'll get like a positive result here. And so let's do this integral. Let's do b dot ds around this loop here. Let's start here. This will be the easiest thing to do. We're outside the solenoid, so magnetic field is zero here, so that contributes nothing to the integral. Again, we're saying the magnetic field outside the solenoid is zero, so that does nothing. This does nothing. So far we have 0 plus 0 plus 0. But now inside the solenoid, we have B times the length of the solenoid. So B is constant inside the solenoid in both magnitude and direction. So we can take that out, and then we have the integral of ds, which is just L. Okay, that part is easy. And so according to Ampere's law, we have B times L is equal to mu naught times the current. Now, what current are we talking about? We're talking about the current that's crossing this, this region defined by our curve. Now, the current in the wire is I. However, it's crossing multiple times. So let's say that N is the number of times that this wire, basically it's the number of loops we have. So again, if we look at the whole solenoid, you can just like count loops going down the solenoid. N is the total number of loops. And if we solve for the magnetic field, we get B is equal to mu naught Ni over L. Now, this is usually written this way. Mu naught lowercase n times I. I'm going to write that here. Where lowercase n is called the turns ratio. That'd be like the number of turns per length. So it could be like, you could have a solenoid with, say, a turns ratio of 100 per centimeter. So if you look at it, that would be kind of high. Let's say 40 per centimeter. So if you just take like 1 centimeter of the solenoid, count the loops, there'd be 40. And again, it's kind of uniform. They're closely packed together. So usually it's expressed in terms of this lowercase n. So yeah, that would be the very simple result. Getting there, maybe not so easy. We had to use Ampere's law 3 times and make a few approximations, but they're very reasonable approximations, and this works out pretty well in practice. And what's nice about a solenoid, one thing that's nice about it is that we now have a way of creating a constant magnetic field. We've used applications of this before, like in a mass spectrometer or blanking on the name, the cyclotron. That had a constant magnetic field, and now we know how we can create those. Just like we can use a capacitor to create a constant electric field, we can use a solenoid to create a constant magnetic field. And there's actually another very important thing about solenoids, which we're going to come to later. We're going to talk about something down the road called Faraday's law. And solenoids are very important there. So we're going to come back to solenoids later. But for now, let's do a quick calculation and find the magnetic field. Let's actually let's imagine that we take this solenoid and run a current of 10 amps through it. So let's see if we can figure out the magnetic field we could create. Oh, by the way, we would call this an electromagnet because, like right now, there's no magnetic field inside here. Oh, I mean the Earth's magnetic field, which exists everywhere. But if we run a current, that creates a magnetic field. So the electric current creates a magnetic field. It's called an electromagnet. And let's say we create a current of 10 amps. Now I'm going to try and approximate, I'm just going to count. I'll approximate a centimeter and try to count the number of turns. Around 25. Obviously I wasn't being too careful with counting, but I'm fairly confident that that's a reasonable number of turns per centimeter. So, yeah, if we run a current of 10 amps, what kind of magnetic field are we going to get inside? Let's do that. Let's just calculate it. It's a kind of trivial calculation. So we have mu naught. Let's do the 1.26 times 10 to the minus 6 Tesla meters per amp. N is 25 per centimeters. So let's convert to meters. And then the current is 10 amps. And let's say there's 1,000 milliteslas in a Tesla. And then this is a very easy calculation because let's look at the units. I mean, we could actually just visualize it, but why not write it out? So on top, Tesla, meter, centimeter, amp, milliteslas. On the bottom, we have amp, centimeters, meters, and Tesla. So we'll get a magnetic field in milliteslas. So we have 1.26 times 25. And then here we have 100 times 10 is 1,000. times 1,000 is 10 to the 6. So we're done. That cancels out the 10 to the 6 on the bottom. Nice, we had 10 amps, a nice even number. So let's just do this. 1.26 times 25. Can actually simplify that a little. Now let's just do it the long way. Who cares? We could multiply by 4 over 4. So we'd have 1.26 times 100 divided by 4. Probably a little bit easier, but so what we're getting is 31 let's just say 32 milliteslas. So that's what we get inside the solenoid. And not too bad. We need to run 10 amps through it. It's fairly significant current. But yeah, still we're talking milliteslas here. Now we could actually increase that value by putting metal inside of this. And we'll talk about magnetic fields in matter, but if you put like iron inside here, it would magnetize the iron, and or many metals you can put inside here that could magnify the magnetic field inside. But 32 milliteslas, I think that's a little better than like a standard bar magnet. Reasonably significant magnetic field. Okay, so we'll stop here, and another application of Ampere's law is torrid, but we'll do that in a separate video.